All right, welcome back to the part 2 video on ionic compounds. So just to sort of recap what we did last time, we learned how to determine the chemical formulas for ionic compounds and also how to name them, okay? What we're going to be doing today is we're going to be doing basically all of the same things, except we're also going to be incorporating transition metals and polyatomic ions, okay? So if we take a look at the periodic table, what I mean by incorporating transition metals is talking about this group of elements here, okay? So these elements here are called the transition metals. They do not follow that pattern that we were using previously, right, with the ionic charges being +1, +2, +3, etc. That is not a guarantee with the transition metals. And there's reasons for that, right? The number of valence electrons actually cannot be used to accurately determine what types of ions these transition metals are gonna adopt. So we're gonna talk about that. We're also going to be looking at polyatomic ions, okay? And that's actually where we're gonna start. So polyatomic ions are different from monatomic ions, okay? And the prefix there, mono versus poly, kind of tells you what the difference is. Monatomic ions consist of a single atom, okay? So this could be like a sodium ion, a chloride ion, calcium, or nitride, okay? This is just a single atom that has a net positive or negative charge, right? Polyatomic ions are still ions, but they're made of multiple atoms. And the way that these polyatomic ions work is a little bit complicated. They're actually covalently bonded together, but as a unit they are an ion, so they have an overall charge. We haven't learned about covalent bonding yet. We're going to get there. We'll look at some of these polyatomic ions when we do get there. But long story short, these polyatomic ions can be treated exactly the same as a monatomic ion. They're just made up of multiple atoms. They still have an overall charge of, say, +1 in this case, or -2, or -3, okay? So, ionic compounds can be composed of monatomic ions or polyatomic ions or both. The same rules apply when determining the formulas. Okay, ionic compounds must be electrically neutral. Okay, so let's look at some examples of this. Let's go to the next slide here. Oh yeah, sorry. Here's a big list, by the way, of polyatomic ions. These are all the polyatomic ions I'm going to expect you to be able to work with. You don't have to memorize this. Okay, so this is like a list that I'm going to have posted on Canvas, or you can find in these slides here. These are the names along with the formulas and the charges for these different ions. You'll notice that the vast majority of these ions are negatively charged, right? All of these here have a charge of -1. The purple ones here, charge of -2. Yellow, charge of -3. And this single green one down here is the only one on this list that has a positive charge. There are a few other ions that aren't on this list that you know we could potentially run into, and in that case you could simply Google them, right, and figure out what's going on there. But this list encompasses most of what you're going to ever be exposed to. Okay, so let's look at a few examples of how to work with these polyatomic ions. All right, so as we discovered previously, right, the first thing that you really need to do, if you have the name of a compound, you need to figure out, like, what is that made of, okay? So potassium, all right, that's going to be a monatomic ion with the symbol K. And if I look on my periodic table, potassium is in that first column on the periodic table. It's going to have a charge of +1. This is how we can write that, by the way, just with a plus sign. If it was +2, for example, I would need to write +2. But if it's +1, I'm allowed to just write a single plus sign. You're also more than welcome to write +1. Okay, both are fine. Just to let you know, though, sometimes if you will see, like if you're on a website or in a textbook or something, you may only see K plus rather than K +1, but they mean the same thing. Okay, sulfate is a polyatomic ion. Notice that this is not sulfide. Okay, if this was potassium sulfide, then this ion here, sulfide, would be referring to sulfur, a monatomic ion of sulfur, right? Because that's what that IDE suffix tells us, right? So like fluoride here, this is going to be an atom of fluorine. Sulfate is something else, okay? And what is it? It's a polyatomic ion. So what is its formula? Well, if you consult that list on the previous slide, you would see that sulfate is SO4 with a -2 charge, okay? Also, by the way, you may see me write things like this, 2-, or you may see me write them like -2. It's really not a big deal. I think this is technically the proper way to write it, so really this should say 1+ or just the plus sign here. It's not a big deal, okay? So 2- or -2, it doesn't really matter. Okay, so here are the two components, the cation and the anion, the positively charged ion and the negatively charged ion. We still have to follow the same rules, though, to come up with the chemical formula. So we need to consider, right, what ratio of these ions do I need to make a compound that is electrically neutral? Okay, well, if a sulfate ion has a charge of -2, then I must need 2 potassiums along with that one sulfate ion to have an overall charge of 0. Okay, so this right here would be my formula for potassium sulfate, K2SO4. All right, perfect. All right, let's move on. Next one is ammonium fluoride. Ammonium is not an element. Okay, this is it's not aluminum. Okay, it's ammonium. Ammonium is the only positively charged polyatomic ion on that list. There are a few other positively charged ones, but the only one that was on that list, the most common one that you're going to see, is ammonium. Okay, so this is NH4 with a positive charge, +1. And then fluoride, as I discussed earlier, because it's got that ending IDE, fluoride is referring to the monatomic ion of fluorine. Okay? So, +1, -1, this is an easy one. Okay, we just need one of each ion. Okay, so my formula here is NH4F. Okay, remember that the formulas and the names always go in the same order. It's the positive ion first and the negative ion second. Okay, so there we go. That's my formula for ammonium fluoride. All right, and then our final example here, aluminum hydroxide. Okay, aluminum is an element. Based on its position in the periodic table, I know that aluminum is going to have a +3 charge. And hydroxide, this one is a tricky one, okay? I know it ends in "ide," right? And we just got done talking about how "ide" is an indicator that it's a monatomic ion, right? Like sulfide would be sulfur, fluoride would be fluorine. Well, what would hydroxide be? Would that be hydrogen, or would it be oxygen? Turns out that it's neither, okay? Hydride would be hydrogen, oxide would be oxygen, hydroxide is actually a polyatomic ion. So even though it ends in "ide," it's actually a polyatomic ion that consists of both oxygen and hydrogen, and it has a -1 charge. So things get a little confusing. Just be on the lookout for that, okay? Only hydrogen would be hydride, and then only oxygen would be oxide. These would be monatomic ions of hydrogen or oxygen. We're looking for hydroxide, which if you consult that list, you can find hydroxide on there. It is a polyatomic ion with a -1 charge. Okay, so my ratio here, I must need 3 hydroxides to balance out the +3 charge from aluminum, right? +3 charge on this single aluminum ion, I need 3 hydroxides. Okay, so how do I write this? Well, I've got 1 aluminum, and then I have 3 hydroxides. Now, you might be tempted to just write this, right? AlOH3. This is technically not correct, because what this means 1 aluminum, 1 oxygen, and then 3 hydrogens. That's actually not what we need, right? We need 3 hydroxides, not just 3 hydrogens, right? We need 3 oxygens as well. So this is technically incorrect. The way to write this, okay, is like this, right? If I need 3 hydroxides, I'm going to put this in parentheses and put my number 3 on the outside of the parentheses there, okay? So Al, open parentheses, OH, close parentheses, 3. This means 1 aluminum and 3 of what's inside here, 3 hydroxides. Okay, so I think that's a pretty comprehensive list of examples there that show you all the different possible quirks and weird things that you may run into when working with polyatomic ions. Okay, let's move on to the next subject here, which is transition metals. Okay, and transition metals, like I mentioned before, those are those elements that are in the middle section of the periodic table. The transition metals break some of the rules. Okay, so let me just read here what this says. Transition metals and elements with 4 valence electrons, meaning lead and tin and lead, okay, I'll talk about that in a minute, those can form ions as well, all right? However, we can't use the patterns on the periodic table to easily determine their ionic charges, right? So if I back things up a little bit, remember I had drawn like the +1, +2, +3 charges on here. I can't draw those on the transition metals. Okay, they don't follow those nice, neat patterns. It's a bit more complicated than that. So if I want to know what the ionic charge is for a transition metal, I have to sort of be given it or I have to determine it. Okay, and let me show you some examples here. All right, if you're given the name of a ionic compound that involves a transition metal like iron, then the ionic charge for that element is going to be given by Roman numerals in the compound name. Okay, so iron 2 oxide, this Roman numeral 2 is referring to iron. And in this example here, iron 3 oxide, this is referring to iron as well. Iron is one of those transition metals, and it can actually have multiple different ionic charges depending on, the compound. So iron 2 oxide would be composed of Fe2 plus, or +2, and then oxide, which is 2 minus. Okay? The formula then for iron 2 oxide would be FeO. Right? I would need 1 iron +2 and 1 oxide -2 to balance out the charges, right? And so this would be my formula. Okay? But let's look at what would happen with iron 3 oxide. Iron 3 oxide has a +3 charge. That's what that Roman numeral tells us here. Okay? Oxide is still going to be the same, 2 minus. And so to determine the formula for this, it's a little bit more complicated. It turns out that I need 2 irons and 3 oxides to get that electrically neutral compound. So that's my formula there. Okay? Those are 2 different compounds that do exist in reality. Okay, you have FeO and Fe2O3. Iron 2 oxide, iron 3 oxide. They're 2 real things. Iron can adopt multiple different ionic charges. Okay, and that is true for several of the different transition metals. Okay, it's also true for some elements that have 4 valence electrons. You may remember me talking about this last time. The elements that have 4 valence electrons, carbon, silicon, germanium, those 3 tend to not form ions, but the bottom 2 can. So that would be tin and lead. And basically, it's the same rule. We're still going to use these Roman numerals. So let's look at an example where it's sort of flipped around. Let's look at this formula here, PbO. Pb is the symbol for lead. We're going to try to name this compound, okay? Well, Pb, I'm not sure what ionic charge it's going to have, but I do know that oxygen, based on its periodic table position, is going to have a charge of -2, okay? So I know that. I know oxide is going to be -2. Oxide is always -2. But what is this charge going to be on this lead? Well, this formula has these ions existing in a 1-to-1 ratio. So if oxide has a charge of -2, this lead must have a charge of +2, okay? You see how that works? If I have 1 lead and 1 oxide, and I know that oxide has a -2 charge, then this lead must have a +2 charge. Turns out the name for this formula is lead 2 oxide. Okay? And I was able to determine that once again because I know the formula, or I know the charge on oxygen. I know they're in a 1-to-1 ratio here in the formula, and so I know that lead must have a +2 charge. Okay? Now, if I look at this other compound, once again, these are both real things. If I look at this other compound, 2 oxides, right? That would be O2 minus and then another O2 minus. Well, then what would the charge need to be on the lead, right? This compound overall has to have an overall charge of 0. So what would the charge have to be on the lead? That's right, it has to be +4, right? this is a combined negative 4 charge. This must be a positive 4 charge. So the name for this one would be lead 4, or IV, right? Roman numerals, lead 4 oxide. Okay? So Roman numerals are used whenever you have transition metals or elements that have 4 valence electrons. Tin can do the same sort of thing, as do a lot of other transition metals like copper and zinc and gold and iron and chromium and all the other transition metals. Many of those can form different ionic charges, and so we need those Roman numerals to be able to deal with them. Okay? So in today's assignment, you're going to be working with transition metals, and you're also going to be working with polyatomic ions. Okay? And we'll do some examples of these problems in class before you get started on your assignment. All right, thanks a lot for watching, and I'll see you next time.